Hey guys, welcome to Unit 4, Covalent Bonding and IMFs. We are looking at Section 1, Covalent Bonds and Polarity. So we're going to go through a little bit more detail about covalent bonds to add on to what we did in class today, as well as looking at what it means for a molecule or a bond to be polar. As a reminder, covalent bonds share electrons, so we see that both electrons are accessible to both atoms, whereas in an ionic compound, the electron actually will fully transfer onto the other atom, causing that electrostatic attraction between the two now that one is positive and one is negative. So with covalent, they both are attempting to essentially form negative ions because they want to gain the electrons, but neither of them are willing to lose, so they just share. So those elements that are sharing those electrons are going to be two nonmetals. Of course, as mentioned, we could have more than two, but they're traditionally just going to be nonmetals. They're both trying to gain electrons to fill that energy level, so they're just going to share. We have no ions formed in covalent compounds, so they do not conduct electricity as solids, nor do they as an aqueous solution. Traditionally, a single covalent bond is going to be two electrons being shared, so if they both need the electron, then they're just going to share the two electrons between them. That can actually be a single bond, but let's say two atoms have 4 electrons that they both need to share, okay? So like, let's look at oxygen, for instance. Dot, 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 single, single. Another oxygen, dot, 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 single, single, okay? We know right off the bat that when we have an unshared pair, they are that, unshared. So those are going to stay open. But oxygen right here would like to share those two, and oxygen would like to share those two, because then the oxygen on the right is going to have 1, 2, 3, 4, 5, 6, 7, 8. The oxygen on the left is going to have 1, 2, 3, 4, 5, 6, 7, 8. So why not just share two sets of electrons? We show that by having two actual bonds written between them. Okay. If that needs to happen 3 times for them to be satisfied, like an example with N2, then it's called a triple bond. Single bonds are relatively weak compared to double bonds and triple bonds, and it makes sense because every time they share a set of electrons, it draws them closer together, makes them more associated with each other, more attracted to each other. So triple bond is going to be very strong and very difficult to break. Now we said covalent bonds form when atoms share electrons, but not every atom has the exact same electronegativity value. Some are more interested in electrons than others. And so they don't always share electrons evenly. Sometimes they're going to be a little bit greedy if they are more electronegative. So what we really see is that in covalent bonds, there's 2 major types. There's nonpolar covalent bonds and polar covalent bonds. Polar basically just means that we have a positive and a negative end to some sort of thing. So what I've just drawn here, this would be polar. If I drew it with no charges, that is nonpolar. Okay, essentially, neither end of the circle is going to be charged in any direction. So nonpolar covalent bonds means that the atoms are equally sharing their valence electrons. So both elements are pulling on them. The electrons are going to be located right in the middle of the bond. So looking up here at the top, hydrogen and hydrogen, they both have the same electronegativity. They both want the electrons just as much. So the electrons are going to be essentially in our mind thought of as being in the middle, okay? So each of them has equal access to them. In a polar covalent bond, one of them has a much higher electronegativity than the other. So they are not evenly sharing those valence electrons. So in the other image up here at the top, fluorine being more electronegative, the electrons are going to be drawn way more towards fluorine, which, by the way, if you look sideways, it looks kind of like a mask, like a Halloween mask. You know, it's like got a mouth right here. Anyways, all right, sorry. Go back. Okay, so polar covalent bonds means that they are not evenly sharing. One of them has much more access to the electrons than the other would. Now, in terms of what that ultimately means, electrons are negative, right? So if in this image up here at the top with the polar covalent bond between hydrogen and fluorine, if the electrons are further towards fluorine, that end is going to become slightly negative. The other end will become slightly positive. Are we recalling any other situation where this happens? It's water. Okay, so we talked about that. Water has The oxygen is negative. The hydrogens are both positive. That's how it is actually used to dissolve ionic compounds, because the positive ends will attract the negative ions, the negative end will attract the positive ions. That's because the electrons shared between oxygen and hydrogen are much closer to oxygen, giving that end of the bond a negative charge. Okay, that end of the bond is going to have a negative charge. And I'll talk in a few minutes about what these arrows are that I'm drawing and everything, okay? But unequally sharing electrons makes a bond polar because one end is going to have the electrons more than the other. So to determine the polarity of a bond, all you really need to do is figure out how big of a difference is there between the two elements. If one of them has a very high electronegativity and the other one has a very low, the difference is going to be huge, so that means it is extremely polar. If they're pretty close, the difference is going to be pretty small, okay? These ranges are something that we are likely going to want to try to remember, but I wouldn't stress about them because they're on your formula sheet, okay? So being able to tell the difference between nonpolar, covalent, polar, covalent, and ionic, memorizing the numbers, not important. Understanding why the numbers are the way they are, important. So a nonpolar covalent bond where both of them is roughly equally pulling is going to have a relatively low difference between the electronegativities. If the electronegativity difference is much greater, then we're going to have a polar covalent bond. If it is extremely great, that means that one of them is so interested in the electrons that not only is it going to pull it in that direction, it's just going to steal it. Oh wait, that means it transferred? Oh wait, that's an ionic bond, right? So ionic bonds, hold on to your seats, hold on to your seats. Ionic bonds and covalent bonds are all part of the same style of bonds. It's just that ionic bonds, the difference between the two elements is so great because one of them is a metal and one's a nonmetal that they just transfer the electrons, versus something like a polar covalent where the difference is pretty great but not enough to really fully take the electrons off of one of the elements to the other. All right, in practice, let's look at it. So magnesium. Magnesium has an electronegativity of 1.2. Chlorine, so if we look at MgCl2, we know that that essentially means that I have a magnesium and I have two chlorines, Cl. So we have a transfer of electrons because magnesium is a metal, okay? So that means that it has one bond between magnesium and chlorine there, and magnesium and chlorine are bonded there, okay? So each bond is an MgCl bond, so I don't need to do it twice. I just need to say, okay, well, is an MgCl bond polar, nonpolar, or ionic, okay? So magnesium has an electronegativity of 1.2, chlorine has 3.0. When I do that subtraction, I get 1.8. 1.8 is greater than 1.7, so this is an ionic relationship. Now, we've already knew that because magnesium is a metal and chlorine is a nonmetal, but either way, we've now confirmed it based on polarity. Let's look at another example, water, okay? So in the water molecule, we have an oxygen with two hydrogens attached to it, okay? So again, the OH bond here is identical to the OH bond there. So I'm really just looking at what is the electronegativity difference for an OH bond, okay? So hydrogen has electronegative 2.1, oxygen is 3.5. When I do that subtraction, I get 1.4. It's not over 1.7, so it's not ionic, but it is very polar. It's very close to that. So this is a polar bond. What that means is that the one that's more electronegative is going to be having the electrons more often, the oxygen end. The one that's less electronegative or less attractive to the electrons is going to become slightly positive because the oxygen is really hogging the electrons. They're all shifting to that end of the molecule. So what I was just talking about with that shifting electrons and how that changes the charges, that can be visualized with what we refer to as a bond dipole. So when electrons are shared unequally, the ends of the bond are going to end up with a charge. Higher electronegativity is going to have a negative charge. Lower electronegativity is going to have a positive charge. And the dipole vector is drawn as an arrow with a line across it to show the positive end. So let me slide this up. All right. So let's look at water, for instance. So we have oxygen, hydrogen, hydrogen, okay? And we said that oxygen is more electronegative. So what I'm going to do is when I'm drawing a dipole vector, which is what we're doing, vector just means like an arrow essentially, and dipole, di means two, pole means poles, so two poles. So we're showing the positive and negative poles of a bond. So this is a polar molecule, which means that going from hydrogen to oxygen, I'm going to draw the arrow from hydrogen to oxygen, and then I put a line across it at the other end to show that that's the positive end, okay? That means that this end becomes positive, this end becomes negative, okay? The other bond is the same way. The hydrogen is going to be slightly positive, the oxygen becomes slightly negative, okay? So ultimately, this becomes the negative end of the molecule. That is a positive, and down here is a positive, okay? Now, in our next lesson, we're going to be talking about what that means for the molecule as a whole. You may already know, you may already be able to visualize that this is kind of the overall charge, but let's just focus on the bonds for now, okay? Let's look at another one. Let's look at methane. Hydrogen, hydrogen, and I'm doing rough draft electron dot diagrams right now, so don't freak out or anything like that. Don't worry about that. If you're like, well, that one's supposed to be a wedge and that one's supposed to be a dot, whatever, okay, it doesn't matter. So what we see here is that carbon and hydrogen are both going to be, hydrogen has an electronegativity of what, 2.1? Carbon is 2.5, I think. So that means that carbon's a little bit more electronegative than hydrogen. That's not right. Hold on. All is well, it is right. Okay, so that means carbon's a little bit more electronegative than hydrogen. So when I draw a dipole vector from each hydrogen to the carbons, this is how I'm going to draw them. They are all going to become slightly positive at the hydrogen end and slightly negative down at the carbon end. So the carbons will become slightly negative. The hydrogens become slightly positive. Okay, and I like to circle these just so they stand out. Not necessarily a requirement, but it does help to differentiate them from the bonds. Okay, so this is how we're going to close this lesson. We're going to be kind of taking the next step with it in class, but what I want you to recognize is why are molecules polar, or excuse me, why are bonds polar? How does electronegativity play into that? And how to draw a dipole vector on a bond. Figuring out which one's more electronegative, draw the arrow in that direction. All right, I will see you guys next time. Make sure that you work on practice problems 1 through 7. I know there's not a number 6, so 1 through 5 and then 7. And then don't do 8 yet because I'd like to handle it differently. Okay, see you guys next time.